Okay, I want us to work through these problems 1 through 6, and then as much as we can, probably not gonna be able to cover all of it. We did number 1 on Friday. I hope to go through the more difficult ones, and then whatever we don't finish in class today, you guys will show me tomorrow as homework. So tomorrow's homework, I'll be checking 1 through 3 and 4 through 6. So basically 1 through 6 tomorrow. Okay. But you'll count as 2 homework assignments that go into your and get that. Okay, so let's skip number 2 for now, and let's go to number 3. Okay, you're gonna need your calculators. Okay, so these FRQs is what we call rate in, rate out. So there's a couple of things going on. We have to kind of keep track of what's these rates that's accumulating, and you're going to see that we have so a couple of different things occurring at the same time. So let's start off with the original problem. It says the tide removes sand from Sandy Point Beach at a rate modeled by function r, given by r of t. And we definitely want to be always in radian mode, especially if we see any critics involved. And we're never going to be in degree mode. Okay, a pumping station adds sand to the beach at a rate modeled by the function s, given by s of t. So there's 2 things going on. You got sand being removed by the water, by the tide, and then you have a pumping station that's trying to add sand back onto the beach. And both r of t and s of t have units of cubic yards per hour, and t is measured between the hours of 0 to 6 hours. At time t equals 0, the beach contains 2,500 cubic yards of sand. So part A, how much sand will the tide remove from the beach during the 6-hour period? And indicate units of measure. So we want the amount of sand removed. So we know we're dealing with r of t, not s of t, right? S of t is adding sand to the beach. We want information about sand being removed from the beach. So we know we're using working with r of t, but r of t is in terms of what? What's the units for r of t? Yeah, cubic yards per hour, right? So it's the rates. But part A is asking for the total or the amount of sand, which is cubic yards. So how do we get from cubic yards per hour back to cubic yards? What do you do? Take the what? Yeah, antiderivative, right? So, right, so for part A, we can simply take the integral from, and it says in that 6-hour period. So what will be our bounds? 0 to 6, okay. Alpha y equals. Answer.
Okay. Thank you.
Okay. So I want integral of r of t dt. All right, and this should make sense because r of t is cubic yards per hour. dt is in terms of hours, so cubic yards per hour times hour. Right. Anytime we're dealing with integral, you're thinking area of a rectangle, right? That's the easiest area formula. So width times height, that's what we're doing. We're accumulating all these rates over the course of this time period. So we make the calculator do the work for us. So I like to store my information under Y1, Y2. So under Y1, I'm gonna let it hold that R of T. And we're always using the variable X instead of any of the variable that the problem gives us. F9. There's my R of T dt. Okay, 31.816. What's our unit of measure going to be? Yeah, get cubic yards, right? Yeah, 815 or 816. Right, you have cubic yards per hour multiplied by hour. That's why the units change to just cubic yards. Okay, part B, write an expression for y of t, the total number of cubic yards of sand on the beach at time t. So we're going to see some formulas that we're going to see this formula that we're going to use over and over again. So before we introduce the problem for part B, let me write out this formula here, because this will kind of help us keep track of all the things that's going on, because we have to keep track of the fact if we want to figure out how much sand is on the beach, we have to take into account how much there is to begin with, how much is being added, and how much is being taken away, right? So all these moving parts, we want to keep track of all those things. So we're going to see that this formula is going to be useful for a lot of different scenarios. Well, a lot of different problems going to have this setup. So let me write this formula here. So total amounts is equal to the initial amount. So how much you started with, plus the amount added, minus the amount removed. So if I have however much I began with, plus how much I added, subtract how much I removed, then that is what I'm left with, right? My total amount is basically my remaining amount. I think of it as total amount is my remaining amount. Okay, so here's a formula that we can use for this. Once we have it out in words, this is how we're going to establish it. So we're going to say y of t for this, just for this representing the cubic yards of sand is equal to the initial amount. Okay, how much was on the sand to begin with at t equals 0? 2,500. Okay, so that's our beginning. Plus, okay, the amount added. The amount added is going to be related to which function? S of t, but S of t is a rate, so I have to take the what to get it to an amount. Antiderivative. Okay, so antiderivative from 0 to some t value, right? Right now, we want to give it that flexibility so that we can have a formula that will adapt to any time that we want, right? Because it could be total. We could be looking for the remaining amount 1 hour in, 2 hours in, 2.5 hours in, 4 hours in. We want to give it that flexibility. So we're going to say from 0 to t, so we can use it for adapt it for any time that we want. But the only adjustment is that we have to put a different variable in place, because the t is going to get inserted into this variable. So instead of using t, we're going to use x. So 15x over 1 plus 3x dx. And that's just to, yeah, we just have to make sure, it's just a small little thing here, just make sure that there are different variables, so this can be plugged into that. Okay, minus the amount removed. So integral from 0 to t. And then I'll write out my r of t. Oops, sorry, 2 plus. Okay, basically, I'm doing the integral of s of x minus the integral r of x. If I just put the exact formula here. So if I want to figure out how much sand there is 1 hour in, I can just put 1 in for t. If I want to figure out how much sand remains on the beach 5 hours in, I can replace 5 with t, but 5 in for t, and this will tell me how much has been added in that 5-hour period, how much has been removed in that 5-hour period, plus however much I have to begin with, and that will give me my amount at that time. So all it's doing is asking for an expression. So it's really this problem is kind of building towards the end that we want to use. So it's kind of just asking us to gather information so that we can use it for future parts. Okay. All right, any questions there for part B? Okay, part C. Part C says, find the rate at which the total amount of sand on the beach is changing at time t equals 4. So if y of t is the amount of sand, then rate at which total amount of sand is changing, we want what? Instead of y of t, we want y prime. Yep, we want y prime. So basically, they set us up for part C because, okay, so here's my y of t, and now I'm going to build my y prime of t, which will be the rate of change that the amount of sand is changing. And so I'm just going to take the derivative of everything that I see in front of me. Okay, so y becomes y prime. 2500 becomes what? 0, right? It's constant. Constant goes 0. Plus the derivative of this. What's going to happen if I take the derivative of this integral? Yeah, cancel. Yeah, second theorem, right? So we know derivative and integral, which is wipe each other out. The t will get inserted in for x. So really, it's just going to be s of t. Okay, I'm just going to go back and write the function, and so that I don't have to just refer to the function, and I can call it later. But essentially, I'm taking the derivative of this integral, right? So that's what's happening here. I'm taking the derivative. Right, everything is going to get applied this derivative process. Same thing here. I want to take the derivative of this integral here. So this will give me just becomes minus r of t. All right, any questions with how we built our derivative? Okay, so if I want to figure out what's the rate at which the sand on the beach is changing, I just do s of t minus r of t. All right, and if s of t is larger, then I'm getting a positive value. If it's getting a positive value, then I know that at that time, the sand on the beach is going to be growing. And if r of t is higher, then I'll get a negative value overall. And negative value will mean that y prime will give me negative, which means that at that time, the sand on the beach is going to be decreasing. All right, so now this part C. Find the rate at which the total amount of sand on the beach is changing at time t equals 4. We have our formula. Now we replace t with what? 4. Yep, y prime of 4 is equal to s of 4 minus r of 4. Okay, so I'm just going to go ahead and put s of t and r of t into my y1 and y2 because eventually I'm going to have to call this again. I don't want to keep typing it in. So I have r stored. I'm going to type s as y2. Again, I'm always going to use x variable. So it's just going to be S of 4 minus R of 4. So S is stored under Y2. So I'm going to do now a trace, select Y2. So I get negative 1.908. Okay, what's my unit of measure going to be? Well, yeah, cubic yards per hour, right? S and R, they're both in terms of, they're both rates, right? They're both in terms of cubic yards per hour. So this is going to stay cubic yards per hour. So what does that tell us? At time t equals 4, when it's 4 hours into this time period, what's happening to the sand on the beach? It's decreasing, right? The amount of sand on the beach is decreasing by 1.908 cubic yards per hour. They're both occurring, right? Sand is being added, sand is being removed, but the amount removed at that time is at a higher rate than what's being added. So at this moment in time, the amount of sand on the beach is going to be shrinking. Okay, questions so far? Okay, for part D, for between 0 and 6, at what time is the amount of sand on the beach a minimum? Okay. When is it at a minimum? We talked about yesterday how if we want to find max and min, we just set the derivative equal to what? 0, right? Now it could be max, but we know that at least when slope equals 0, there's potential for a minimum. But there's another thing that's going on here. We don't see the word here, but the understood word here, or it's understood that it's not just a minimum, it's asking for the absolute minimum, okay, on this entire time interval. Which means, if you remember from first semester, this is what theorem here. EBT, yeah. So EBT says, if I want to find absolute minimum or absolute maximum, I have to involve not only relative max and min, but I also have to rely on what S candidates. Endpoints, yes. So this is kind of first semester coming back in again. So I got to involve endpoints and got to involve critical points. And critical points just means setting the derivative equal to 0. Okay. So we have y prime. So let's set y prime equal to 0. So I'll replace 0 in for y prime. So 0 is equal to S of t minus R of t. Okay. Now, one thing that we could do, which is fine, it just takes a little bit longer, is that if I want to find S of t minus R of t, I don't want to solve it algebraically, but if you plug in the calculator, you could graph S of t and R of t and see where they intersect. You could do this. This is legitimate. And just solve for t where they intersect. But the problem here is that if you do this, the graphs may be kind of all over the place, and searching for an intersection between two graphs, that can take a long time, especially if you want to zoom in and zoom out and trying to figure out, where these graphs are intersecting. I think the easier way to do this is graph this instead. Graph S of t minus R of t, and then just look for the what? X-intercept. I think that's a little bit easier because you know where the x-intercept is. You just have to kind of maybe extend out further along the way, but really you shouldn't have to extend too far because any t value you're looking for is between 0 and 6, right? It's got to be some time in that interval between 0 and 6, so it shouldn't take that long. But we're going to create S of t minus R of t just to see what that looks like. Now, in my graph, I don't want to recreate all this function that I typed in. So I'm going to go to the equal sign. You see that equal sign? I'm going to unhighlight it by hitting enter. That just shows that I don't want to see the graph. for just S of t and R of t. I want to see the graph for S of t minus R of t. So it's going to be y2 minus y1. So I'm going to do y2 minus y1, alpha trace minus y1. I want to graph this. I want to do zoom 6 just to see what it looks like. It may be too zoomed out, but zoom 6. Okay, so it's actually not bad. We can kind of just scroll to that point there. Right? Okay. So we know that we're looking for an x-intercept. Wherever it changes signs is going to be a potential candidate that we have to involve. So you can zoom in if you'd like, but looks like I can get to that point without having to zoom in. So if I do second trace, I'm looking for an x-intercept, so I'll select 0. Okay. I'll pick a point to the left of the x-intercept. Okay. Hit enter. Scroll over to a point on the other side of the x-intercept, hit enter. Now the calculator is going to find that, try to find that x-intercept for me. So 5.117. So that's a t-value I have to involve. That's a potential place where a absolute minimum could occur. But that's the only t-value, right? There's no other, there may be an x-intercept there, but we don't see it crossing, right? If it doesn't cross the x-axis, it's not a relative max or relative min. So we have one critical point. What endpoints do we want to test? 0 and 6, right? Those are the endpoints. So we want to find how much sand there is at t equals 0, t equals 5.1, and t equals 6. And then we can call back to this formula that we created for part B and just use this formula, right? This will tell us exactly how much sand is on the beach at any moment in time. So we'll do this 3 times. We'll do y of 0, we'll do y of 5.1, we'll do y of 6. Now y of 0 is actually easy, right? How much sand is there to begin with? 2,500, right? Now, if you use this formula, it'll still work. It just, if you plug 0 in for t, right, 0 to 0, that'll go away, 0 to 0, that'll go away. I'm just left with 2,500. But that's also what is stated in the problem, right? The beach contains 2,500 cubic yards of sand at t equals 0. So that's a quick one that we can find. So now let's find the critical point one, 5.117. So we want to include 2,500 plus however much is added in that time interval. So from 0 to 5. I'm going to go back and just call it S of X. So I don't have to keep writing it, but my calculator will just do all that work for me. Like minus the integral, sorry, 5.117. Okay, so this is going to tell me how much sand has been added to the beach in the 5-hour period. I'm going to subtract however much sand is being removed in that 5-hour period, and then add it on to how much sand there is to begin with. All right. So I'll go to my home screen here. It's nice to have my S of X and R of X all stored under Y1 and Y2, so I don't have to keep, typing everything in from scratch. So I'll say 2,500 plus math 9, 0 to 5.117. I have my Y2 holding my S of X. So alpha trace Y equal Y1. Oops. Sorry, I should have put Y2 here. Okay. Y2 comes first. Oops, my bad. Y1 is here. All right, so it should be 2,500 plus the integral from 0 to 5.117 of the amount added minus the amount removed. Okay. So We have 2492. That's the amount of sand at 5 hours in, 2492. So to begin with, there's 2,500 cubic yards. 5 hours in, there's 2492 cubic yards. So now we want to also do y of what? 5.6. Yeah, that's our last candidate. So that's 2,500 plus 0 to 6 of s of x dx minus 0 to 6 of r of x dx. So if you want, you can just go back and recall the same thing that you did before and just change the upper bound to 6. That could save some keystrokes there. $24.93. It's a little bit more, so we know the least amount of sand is going to be at this 5 hour period. Right? Okay, so therefore, the absolute minimum of sand in this 6 hour period is 2492.369 cubic yards at t equals 5.117 hours. So I do like this problem because this seems to be a good model for a lot of these rate in, rate out problems that has shown up in in the last 5-6 years. So we just want to be familiar with this type, and if you kind of understand that the kind of of course not every problem is going to be the same, but it's nice sometimes when it kind of follows this. So we're just kind of targeting the problems that we feel are the most common, and then just kind of get really comfortable with those, and in the hopes that they will show up on the AP exam. But it kind of follows this model where you create this formula, you find the derivative, and then you involve EBT to find your answer. So this type of a model does seem to be pretty common. So that's why I want to spend a day or two kind of going over this type of problem. Okay. Any questions so far about the flow of this problem or any parts that we went through? Okay. Let's see. I think I want to do the more involved ones. I feel like number 2 and 4, hopefully you guys can work through it on your own and with the key kind of figure things out. The other challenging one I think is number 5. So let me go to number 5 for us to do in class together. Okay, so the amount of water in a storage tank is modeled by a continuous function on time interval between 0 and 7 hours, where t is measured in hours. In this model, rates are given as follows. The rate at which water enters the tank is given by f of t. Okay, now this is gallons per hour, so I want to keep. So they like to give these problems. Everything is a rate. Okay. So that's given by this curve here. So we see that the rate at which water is entering the tank is going to kind of gradually increase, right? So initially it's 500 or 0 cubic gallons per hour, and then 1,000 and then 1,000 gallons per hour, then eventually rises to 2,500. So it just keeps increasing. Looks like it's kind of leveling off a little bit up here, but it's going to keep increasing. Okay, so we see water being added to the tank at this continuous rate, or this through this continuous function is continually rising. Okay, but then the rate at which water leaves the tank, okay, is given by this function here. So there's something else going on, right? So there's water being added to the tank, but then at the bottom of the tank, water is being let out at this rate. So it's a constant 250 gallons per hour given by this straight line here. But then all of a sudden, it's going to just switch to 2,000 gallons per hour. So it's just, there's going to be a sudden switch. Okay. And the graph F and G, which intersects at, so this is nice, they give us that intersection, T equals 1.617. And T equals 5.076. So they're doing some of the work for us here. So we don't have to do all the okay, so they got that out of the way for us. At time t equals 0, the amount of water in the tank is 5,000 gallons. Okay, so this is the initial amount. So what I want us to observe right now is I want us to look at this rate and see if we can kind of imagine what's happening to the tank or the amount of water in the tank. Is it rising or is it falling, depending on which is higher? So let's look at between 0 and T equals 1.617. What's happening to the amount of water in the tank? I mean, there's 5,000 to begin with. I mean, there's water being added and there's water being removed. But what do you notice between 0 and 1.617? Which one is higher? The line or the curve? The line. So therefore, what's happening to that water inside that tank? It's falling, right? It's falling because, I mean, water is being added and removed, but if the rate at which water is being removed is higher, then the rate of water, the amount of water is decreasing. So I'm going to just kind of highlight which is winning right now, because in this, in that first hour or so, water is dropping, right? Water, because there's more water being let out than that's coming in. Okay, but then what's happening between 2 and 3? Water level is going to start doing what? Rising, because the amount of water being added is all of a sudden overtaking the amount of water that's being removed, right? So if there's a higher rate of water coming in, then your water levels should be rising. So rising, and this time I'm going to use green to indicate water level rising. But then all of a sudden, right at 3 hours, water leaving, it's going to jump to 2,000 gallons per hour. So now what's happening between 3 and 5.076? Water level is going to go back to what? Decreasing, right? Going to start dropping again. Okay, so I'm going to use this red to indicate which is winning right here. But then after 5 hours, what's going to happen again? Water level is going to start rising. Okay, so that's what I want you guys to have in your mind. Like, okay, you guys are able to look at this graph and kind of visualize what's happening to the water level over this time interval. So it decreases, then it switches to increase, switch to decrease, and it starts increasing again. So I want you to have that picture in your head as we move on. Okay, so how many gallons enter the tank during the time interval between 0 and 7 hours? So this is a little bit easier because it's just asking for something involving F of T, right? We don't care about how much water is in the tank to begin with. We don't care about how much has left. We just want to know how much water enters the tank, and that's just purely with F of T. So I can just take the what of F of T. Yeah, take the antiderivative, right? I want to get from gallons per hour up to hour. So it's just simply the integral from the 0 to 7 of F of T dt. And so typically when you see these FRQ problems, they tend to kind of move you through the problem. They start a little bit simpler, and then they're going to kind of gather information, and it's usually part C and D are usually the more challenging ones, but they tend to kind of start you off. That's usually the pattern. It's not always the case, but you know, the more we do, you're going to see that that pattern with FRQs. Okay, so the integral from 0 to 7 of f of t dt, we go to our calculator, we make the calculator do the work for us. Save this y1 to y3 for the next class, so I'm just going to use y4, but you can erase and use y1 if you like. Okay, so I'm going to use, make sure you're always using variable x, 100x squared, sine square root of x. Dx. Okay, it says round to the nearest gallon, so 8,264 gallons is how much water is going to enter the tank in that time period. Okay, so we talked about this leading up, so the part B should feel a little bit easier now that we kind of talked about the scenario. Between 0 and 7 hours, find the time interval during which the amount of water in the tank is decreasing. So what would you say? Decreasing in which intervals? Yep, 0 to 1.617 and 3 to 5.076. Okay, it's asking for a reason. We just simply say, well, because this is where g of t is greater than f of t. Right? Okay, part C. Between 0 and 7 hours, at what time t is the amount of water in the tank the greatest? All right, so guess what? We have to go through what again? dVt, yeah. So we got to involve the endpoints and the critical points. We kind of know where the critical points are, right? Critical points is going to be at 1.617, at 3, and at 5.076. But it's only asking for the greatest. So that means we have to involve the endpoints and relative max, but what do we not have to involve? The relative mins, right? We don't have to involve the relative mins because, I mean, we can, but we know that it can never lead to the greatest. So we know that water is falling, right? And it's going to start rising here. So we know there's a relative min here. We can ignore this, right? Because water is falling and it's going to start rising. So that's a relative min. But then it's going to rise and it's just going to start falling. So this is a relative max. We want to make sure we include this. But then it's falling, but then it's rising again. So this is a relative what? Relative min. We don't have to include that. Now, if you just went ahead and you test all the critical points, that's not wrong. It just take a little bit longer to get through, but you won't be taking off points because you tested a relative minimum, right? But really, we don't have to test the initial, the end, and the relative max, because we're just only asking for when the tank, the amount of water is at the greatest. But if you wanted to test 0, 1.617, 3, 5.076, and 7, you'll still get full credit. You won't get taken points off because you tested relative minimums. Okay, so again, we're using this formula here. My total amount is going to be my initial plus amount added minus amount removed. Now, you don't have to write this out. You know, if it was on the exam, you wouldn't write this. You don't have to write this out, but I like to right now just have us write it out so we kind of just have some formula that makes sense in our head and we can just fill it in with the specific problems. Okay, so we definitely want to test A of 0. I'm sorry, let me create the formula. Fine. So there's 5,000 to begin with. Plus the amount added. Minus the amount removed. Okay, so let's do A of 0 first. Okay, which is just 5,000. Don't have to do anything more than that. We know that's 0 in for t, we'll just wipe this out. And also we know that's how much there is to begin with. Okay, we're also going to test A of 3. So that's 5,000 plus the integral from 0 to 3 of f of x dx minus the integral from 0 to 3 of g of x dx. Now g of x changes, right? So from 0 to 3, we want to use what? 250 or to 2,000? 250, right? So now we can't just say minus 250. We got to say the integral of 250. Now you could also do 250 times 3, and that's basically what this is doing, right? It's basically taking that rate. It's a constant rate, so it's 250 plus 250 plus 250. So you know it's going to be 750, but it's just I like to just put it into that integral formula, make the calc do the work for us. Okay, so let's make the calculator do the work here. So I'll start with 5,000. 33. I have it stored under Y4 for me. Minus math 9. I'll just enter this in. It's an easy equation here. Just 250. And 5126. Okay, I'm looking for an absolute maximum. So that's a good candidate because this is more than what I had initial, but I'm also going to test A of 7. Now, I think what I would do here for A of 7, because my g of x is changing, right? So why don't I do this instead? What do I do for A of 7? Why don't I just pick up where I left off? Right, because there's a split between 3 and 7. It just kind of makes it a little messier for g of t. So why don't I just say, well, let me just pick up where I left off, 5126.591. Right. This is what's happening 3 hours in. This is how much is in the tank 3 hours in. And then I can just go from where to where for the amount added. 3 to 7. Yeah, I think that feels a little bit cleaner just because g of x is not the same. And that way I don't have to worry about that 250. I already have that 250 kind of taken care of within here. Minus the integral from 3 to 7. And how much, what's the rate for the amount removed? 2,000. Yeah, that feels a little bit cleaner here. Okay, so I already know how much is in the tank 3 hours in. I'm just going to kind of add on to find out more information from in this time period. Okay. We made the calculator do the work. So between these three numbers, we can tell the absolute maximum must be 5126, right? Because we only have three candidates here, 5,000, 5126, and 4513. Okay, so I wanted to get through what I want to get through today, which is numbers 3 and 5. We did number 1 on Friday, so you guys have 2, 4, and 6 to finish. Okay, you guys have the keys as well, and then I'll be checking that tomorrow. Show me 1 through 6, and you get 2 homework credit points added to your next quiz. Okay. All right, come and get your phones. I think I can do it.
This is on the not. Because.
Good, it's just that this gets a little messy.
Yeah.
Then I gotta. Your 3 to 2 shift please, and 7, because key on kind of sketches, it's great. It's not a nice experience. So what I did was, well, I already know how much there is in 3 hours, so why don't I just start at 3 and I just figure out. Oh, yeah, so they have 7 not 55 now.
Yeah.
Because I can think. Yeah, so I could say, and your 7, it's not the same thing as a 3.
Okay, what's like your mind
Plus.
But I couldn't just be like.
Minus 3.
I had to go with someone. Oh, the sun was.
It's kind of stick around.
Like 7, yeah.
Because this is a little messy, that's why I did this.
1,000 steps anyways. Like, yeah, and I just didn't work out. And then in 2 hours, he was like, just walking so much. So yeah. So it's like. There, and then you can always watch them. Oh, you were walking behind the bride. Oh, yeah, she's already lights, like really lights, yeah. And when you saw them like in the. That's so funny. It's like. Show you.